Is the universe really 26.7 billion years old instead of 13.8 billion years? This fantastic recalculation is partly due to the discovery of a Milky Way doppelganger that should not actually exist. The James Webb Space Telescope discovered so many highly developed galaxies in the early universe, shortly after the old Big Bang, that it's almost certain our old theory was wrong. Does this recalculation of the age of our universe provide the answers we seek, or does this new theory raise even more questions that cannot be answered? The James Webb Space Telescope has discovered over 1,000 galaxies in the early universe that are similar to our Milky Way. These galaxies were observed in a time span of a few 100 million to 1 billion years after the Big Bang. This discovery contradicts previous assumptions that disk galaxies were rare or impossible in this era. The disk shape is supposedly the result of frequent galactic collisions. However, at a time when the universe and all the galaxies in it were still in their infancy, there could hardly have been many such collisions. In fact, the number of galaxies discovered by James Webb is too high. These galaxies certainly show signs of young galaxies, but overall they are too developed and too highly organized. If we apply our old standards and ideas of galaxy development to these galaxies, their time of formation would have been before the Big Bang 13.8 billion years ago. The discovery of 3,956 newly discovered galaxies, 1,672 of which have been classified as disk galaxies, forces us to reassess our previous models of galaxy formation and evolution. The researchers, who published their study results in the Astrophysical Journal, emphasized that these findings underline the power and scientific value of the new telescope. They also stressed the urgent need to revise our old theories. The new data on our understanding of galactic evolution and the abundance and stability of disk galaxies in the early universe call into question the Big Bang and other fundamental pillars of astrophysics. In this context, the galaxy Source 2112 is particularly emphasized. SOER stands for Cosmic Evolution Early Release Science Survey, and this galaxy was discovered at a time when the universe was just 1.5 billion years old. Source 2112 shows remarkable similarities with our own Milky Way, which surprises researchers. The Milky Way took billions of years to develop into a disk galaxy with distinct spiral arms. Finding a double at such an early stage of the universe is unexpected. Previous theories assumed that disk galaxies like the Milky Way formed much later in cosmic history. The discovery of Source 2112 challenges these assumptions and suggests that such galactic structures could have evolved earlier and possibly faster than previously thought. One of the strangest features of Source 2112 is its relatively undisturbed structure at such an early cosmic age. Galaxies at this time were expected to be misshapen and chaotic. Nevertheless, Source 2112 shows a surprisingly stable and well-defined disk structure. This raises questions about how this galaxy got its shape and what previously unknown conditions in the early universe made this possible. If we apply our old standards of galaxy evolution to Source 2112, this galaxy would also have formed at a time when the universe did not officially exist, at least not according to our old science. These discoveries suggest a new language that has led some scientists to recalculate the age of our universe. The results are astonishing. Is the Big Bang the truth or a lie? It turns out that there has long been as much evidence against the Big Bang as for it. The problem was that certain theories had been long established and accepted, almost regarded as incontrovertible truths. As a result, some scientists overlooked alternative and equally valid explanations for many space phenomena. Even when discrepancies and gaps in the theories and models became more evident, researchers did not react, stubbornly sticking to what had been considered true since the 1920s. The Big Bang theory, which suggests the universe began 13.8 billion years ago, is based on this old understanding. After the Big Bang, the universe was initially an extremely hot and dense mixture of protons, electrons, and other elementary particles. For the first 380,000 years, the universe was too hot for atoms to exist. During this period, the universe consisted mainly of ionized plasma. As the universe continued to expand, it cooled down, allowing protons and electrons to recombine for the first time to form neutral hydrogen atoms, a process known as the recombination event. The cosmic microwave background, which we use today as a kind of map of the universe, is said to have been created during this phase, helping us reconstruct the early history of the universe. In the 100 million years following the recombination event, the Dark Ages prevailed, a period with no stars or galaxies. The universe was dark and consisted mainly of neutral hydrogen and helium. However, density fluctuations in the universe led to the formation of large gas clouds, which became denser due to gravity. The first stars, known as population 3 stars, formed about 100 million years after the Big Bang. These stars were massive, with masses ranging from tens to thousands of solar masses, and they were extremely bright. After a short lifetime, they ended in supernova explosions, releasing new elements and gases into the universe. These heavy elements were the nuclei for the formation of new stars and galaxies. The first galaxies likely formed by the contraction and merging of smaller gas clouds and protogalactic clumps. Now, thanks to the James Webb Space Telescope, we can see galaxies that have existed since 250 million years after the Big Bang. These galaxies are so developed and structured that they appear as if they have already undergone several billion years of development. This points us in 3 new directions: either the Big Bang never happened and the universe is eternal, or the Big Bang took place much earlier, making the universe much older than previously thought. Alternatively, stars and galaxies evolved in a turbo process. Rendra Gupta, a scientist at the University of Ottawa in Canada, has been exploring alternative models of cosmic expansion and the nature of dark matter and dark energy. Gupta's research focuses on areas that reveal certain weaknesses in our old theories, such as the uniform expansion of the universe and the existence of dark matter and dark energy, concepts that, despite being widely accepted, have never been scientifically proven. The shocking discoveries made by the James Webb Space Telescope have only strengthened Gupta's resolve to challenge the conventional understanding of the universe. He was among the first to dare to reassess the age of the universe, leading to a radical new hypothesis. Gupta's new approach differs significantly from traditional methods, which have largely relied on the cosmic microwave background and the Hubble constant to calculate the age of the universe. The Hubble constant is a measure of the rate at which the universe is expanding, and its accurate determination has been crucial to previous age calculations. However, different methods of measuring the Hubble constant have produced different values, leading to what is known as the Hubble tension. This discrepancy suggests that the expansion of the universe is not uniform, which challenges the current model of the Big Bang and the idea that space has been steadily drifting apart since that event. In an effort to resolve this problem, Gupta developed a model introducing alternative cosmological parameters that reinterpreted the effects of dark energy in dark matter. His model suggests that the universe could be expanding much more slowly or in a nonlinear fashion. A slower expansion would imply that the universe is much older, while an irregular expansion could indicate unknown structures or forces, or even multiple starting points in the cosmos. A key element of Gupta's theory is the modification of Einstein's general theory of relativity. He proposes that dark energy behaves differently over time, which could explain the observed changes in the rate of cosmic expansion. In his first recalculation, Gupta estimated the age of the universe to be 26.7 billion years, significantly older than the previously accepted 13.8 billion years. He also presented an alternative calculation that suggested the universe could be as old as 42 billion years. Gupta even revisited Fritz Zwicky's tired light theory from the 1920s, which posits that the wavelength of light changes as it travels through space. If true, this theory would mean that all previous calculations of the universe's age and the distances within it are likely incorrect. A universe nearly twice as old as previously thought would easily explain the existence of galaxies like Source 2112 and others observed by the Webb telescope. Despite the compelling nature of Gupta's findings, the broader scientific community has been slow to embrace this recalculated age of the universe. Many astrophysicists, particularly those in the more conservative branches, continue to support the traditional Big Bang model, preferring to explore alternative explanations for the James Webb Telescope's discoveries. They suggest that stars and galaxies in the early universe may have formed differently and much more rapidly than we currently understand. However, the debate sparked by Gupta's work is far from over, as more data from the James Webb Telescope continues to challenge long-held beliefs about the origins and evolution of the cosmos. The recalibration of the universe's age proposed by Gupta not only challenges our understanding of cosmic history but also forces a re-evaluation of many interconnected theories in astrophysics. For decades, the Big Bang theory has served as the cornerstone of our understanding of the universe's origins, shaping how we interpret everything from the formation of galaxies to the distribution of cosmic microwave background radiation. Gupta's alternative model, which suggests that the universe could be up to 42 billion years old, fundamentally alters the timeline of cosmic events. This new timeline has significant implications for how we understand the development of galaxies, the formation of stars, and the evolution of cosmic structures, potentially requiring the rewriting of textbooks and the re-evaluation of decades of astronomical research. One of the most intriguing aspects of Gupta's hypothesis is the potential impact on our understanding of dark matter and dark energy, two of the most mysterious and least understood components of the universe. In the traditional model, dark energy is believed to be responsible for the accelerated expansion of the universe, while dark matter is thought to provide the gravitational glue that holds galaxies together. However, Gupta's model suggests that dark energy may not be a constant force and could have changed in behavior over time. This dynamism in dark energy would not only explain the varying rates of cosmic expansion observed but also imply that dark energy is a much more complex and mutable force than previously thought. Such a perspective could lead to new avenues of research aimed at uncovering the true nature of these elusive cosmic phenomena. If this journey has sparked your curiosity, be sure to give us a thumbs up, hit subscribe for more cosmic explorations, and let us know your thoughts in the comments. Do we dare to rewrite the rules of the universe? Until we meet again, keep exploring the unknown, because the universe has many more secrets to share.